Well, hello everyone. I'm John. I'll be your moderator, and welcome to the Natural and Physical Sciences panel. Big welcome to all the panelists, and let's just jump right in. Maybe let's start with each of you just give a very brief 1 or 2 sentence introduction to who you are and what you work on. So let's start with Pete, maybe.
Yeah, okay. I'm Pete Smith at the University of Aberdeen. I've been working on biological sequestration for about 25 years. So I'm interested in all forms of greenhouse gas removal from the atmosphere, but particularly the nature-based solutions.
Awesome. And Nathalie?
So my name is Nathalie Casas. I work at Climeworks as head of R&D. So I'm also working in the field of CCS since about 15 years now. And at Climeworks, I'm responsible for, on the one hand, material research and development, and also process development.
Perfect. And Evan?
Hi, everybody. I'm Evan Sherwin. I'm a postdoctoral research fellow at Stanford University in the Department of Energy Resources Engineering. And I am a founding member of Climate Change AI. I work on, broadly speaking, the role of hydrocarbon fuels in a net zero energy system. And a big part of that is a focus on carbon dioxide removal, particularly for the production of synthetic liquid fuels, looking at in some ways that artificial intelligence can help us develop the next generation of CDR technologies.
All right, awesome. So great. Well, let's maybe start with the question of scaling up in each of your respective carbon removal areas. So starting with Nathalie, how is Climeworks approaching scale up? And especially on the R&D and innovation side, like what is Climeworks' strategy and how has its goals for scale changed over time?
Yeah, that's a very interesting question. So on the one hand, we need to really go to new materials, to cutting edge research, but on the other hand, we are aware of the fact that we need to scale up very quickly. So if we have something in the hand which works well, but is in a very, let's say, lab scale, this is a huge challenge. So we are aware that we need also help for scaling up. So we, especially also in the field of material, we are looking to the outside world and we try to team up or collaborate with companies which can help us to bring really the cutting edge research into a bigger scale very fast.
Your goals look like there? How is Climeworks approaching that, like by 2030 or 2025 or, you know?
Yeah, so we kind of calculate backwards. So if we say we need to have like plants extracting 1 million tons of CO2, for example, by 2025, what does it mean for today? So if this is the case, we need today a material which is already scaled up, because building up a chemical process to produce a lot of sorbent material, so we are working with sorbents, takes time. So we really see at the target we have 2025, 2030, and then we calculate backwards. And this gives the limit of what material makes the race today or tomorrow.
Awesome. So let's go to Pete. When we think about scaling up nature-based solutions, where do we push up against biophysical limits to this scaling? And how has your thinking about this evolved over time?
So we know how to do all of the nature-based solutions because we've been planting trees and tilling the soil for millennia. So it's not really a technical issue, but as you mentioned, there's biophysical limits to how much we can do. So when we look at some of the integrated assessment model projections of removals of several gigatons of CO2 from the atmosphere with methods like afforestation, reforestation, and PECs, we start to run into competition for land. So there are serious issues there with competition for land. You know, hundreds of millions of hectares are required to do this, to get to that sort of scale. So one of the big issues is competition for land. There are some others, you know, there are albedo effects, there are nutrient effects, and there are a few other biophysical limits. But I'd say that these aren't the things that are constraining the uptake of nature-based solutions at the moment. It's mainly the lack of reliable MRV, monitoring, reporting, and verification. I think we'll talk about that a bit more later. I think you're going to ask questions about that later, so I'll leave that for now. But the other one is that, I do a bit of work advising on the science for Carbon Direct. And Carbon Direct have a lot of investment, and they want to get tons, but there aren't enough tons out there. So the nature-based solutions are getting organized into projects, getting the billions of landowners and farmers and foresters in the world organized to do this in a way that they can reap the benefits of the carbon credits is a real big impediment so far to scaling up. So I would say that's the biggest, a bigger issue, in fact, than any technological or biophysical limit. It's the ability to collect land managers together into projects and to put those into credible frameworks, which would then be saleable as carbon credits.
And maybe as a follow-up, how do you think about the whole permanence and reversibility discussion in the soil space and in the nature-based solution space? And how is that changing? How are people thinking about that?
Yeah, so reversibility or non-permanence is an issue, a significant issue which can't be ignored. But I think one can take a risk-based approach to it. So we know that forests can burn down. We've seen it in California just last year, where forests that were carbon credits went up in smoke. So we know that it can happen. And soils can, it's much easier, it's much more easy to lose carbon from the soil than it is to put it in. So those reversibility issues are important. So I think risks-based approaches and also insurance-based approaches where you insure a carbon stock for the future is the way to go on that. I think we tend to now talk about durability rather than permanence. So I think you can regard things in terms of very high durability to poor durability. And then I think you can assess any of the options against each other on a continuum. And different customers will have different requirements.
Right, makes sense. And then moving to Evan, you worked on a paper that sort of compared or looked at the overlaps between machine learning and carbon removal. So I guess my question for you is, where do you see those overlaps and how can machine learning be used to scale up carbon removal? And also, have you seen any new use cases since writing that paper?
Absolutely. So the paper John's referring to is the Tackling Climate Change with Machine Learning report that I produced together with my collaborators primarily at Climate Change AI. We can put a link to the chat if you'd like. Right after, I'll do that right after. And for carbon, so basically in this paper, we looked at all the major areas related to climate change and this is of course an enormous suite of areas: electric power systems, transportation, carbon dioxide removal, and more. And looked at what are ways that we can use machine learning and artificial intelligence to address some of the important questions here. And the real motivating factor here was that we realized that there was so much enthusiasm and energy in the machine learning community of researchers who really, and practitioners who really wanted to help address climate change, but weren't quite sure where to start. So we wanted to help point in the right direction. For carbon dioxide removal, there were a few things that really struck out. So of course, for carbon dioxide removal, there are a few different kinds. There's direct air capture, which Nathalie has been talking about. There are these various natural systems, and then there's the sequestration component, which is of course somewhat separate from the capture component. So sequestration being putting carbon dioxide that you've pulled out of the atmosphere into the ground. Some people call it storage. I like to use the term sequestration because it's going down in the ground, and the goal is for it to never come out again, as opposed to storage where you might want to take it out at some later point. For carbon dioxide removal, the primary area that what I think is the most promising area for machine learning is something that both Nathalie and I should have remembered, Joseph brought up, which is the question of developing new materials. In materials discovery, so there are, of course, the number of materials that humanity could make is pretty much infinite. We can combine all sorts of different things and have materials with slightly different properties. And what we're looking for in this case is, certain types of absorptivity to carbon dioxide, or adsorptivity, I guess would be the word. Something that's going to bind to carbon dioxide in the air, something that's not going to take too much energy to release the carbon dioxide, something that's going to last a while. There are many different properties that one would want to have in a material, and of course this is a new application, so we may not have the materials that are most useful for this right now. And what machine learning can do there is, well, first let's look back at the question, how did we discover materials in the past? That's pretty much been the Edisonian approach to materials discovery, which is when Edison wanted to, well, at least the folklore is, I haven't verified this exactly, but the folklore is that when Edison wanted to figure out how to make light bulbs, he just tried a bunch of different things. Let's see if we run electricity through this material, through this material, through this material, and eventually found something that worked pretty well. Tungsten filaments in that case. And that's not so different than the way materials discovery is often done today. Just try a lot of different things, and oftentimes it's more informed than that. There are computational techniques such as what's called density functional theory, which can guide the types of materials one tries. But with machine learning, we can get a somewhat more informed approach. And I'm not sure how. Let's see. Let me know if I'm going on for too long. But with machine learning, we can start to have an adaptive approach to basically the sampling strategy that we use, where we try certain material combinations, and we can see, well, we tried these ones, then we tried the second set, and then it looked a little better in these parameters, maybe a little worse in these. These are the things we changed on the inputs. These are the things that changed on the outputs. And we can use a variety of approaches, sometimes Bayesian methods, to get an idea of, well, given the information we have, what's the next set of materials that we should try. And there are groups such as Jeffrey Long's group in chemistry and chemical engineering at UC Berkeley, as well as in collaboration with Miguel Gonzalez in electrical engineering and computer science at UC Berkeley. We're doing something along these lines in the development of metal organic framework carbon capture materials. I'll conclude there for now.
Evan, I'm curious, Nathalie, does that describe how Climeworks approaches sorbent selection or process design? I mean, I know Climeworks uses a modular solid sorbent system for direct air capture. So is that design evolving, and how does it work?
So we work with 5 types of sorbents. So we always refer to it as a portfolio of sorbents, being amine, carbonates, MOFs as well. And there we have a test center in-house where we test materials. So we do our own development. So with amines are quite well known. You can tune them, you can make them better. And we understand quite well which parameters need to be tuned. So it's not trial and error per se, but of course we know in which direction we need to go. We produce one material, we test it. So it's a focused try and error, I would say. It's not an AI approach, but it's so we know where we need to go, but we don't know which one is the best. And also with new materials, with MOFs, we approach researchers all around the world to get their material, to test them in-house, so to make sure that we really get the best out of what's out there, because we have a small team in-house, and we know that we might not find the best one if we just stay in-house. So these are how we approach the challenge.
And building on that, I'm curious, I know this is a big discussion in the direct air capture world about the sort of trade-off between sort of innovating with new materials versus sort of just scaling up what we already know how to do. So where does Climeworks weigh in on that, and how does your approach sort of match one of those sides or both?
I think we do both. So we have 2 teams in-house. One is the sorbent industrialization, which is tackling the upscaling. So if there is a material which passes, so in my team, we rather do the research and development. So we have a lab scale, we have a mid scale, and then we have the pilot scale. And if a material went through all the 3 scales and was proven to be better what we have today, it goes to the other team, the industrialization team, which needs to make sure that we produce it at big scale. So we need to do both in parallel also. So when a material moves from lab scale to mid scale, they already come in and try to find solution how this can be upscaled.
Got it. Thanks. Okay, I want to talk now about some of the tools required to make this scale up happen. So let's go back to Pete, because you alluded before to this, one of the biggest pieces of the soil carbon sequestration conversation, that being MRV, or monitoring, reporting, and verifying how much carbon is actually stored in the soil. And it's a huge challenge. So can you maybe talk a little bit about how this works and how you think about it and what you think long-term solutions might look like?
Yeah, sure. So monitoring, reporting and verification is easier for forestry because you can see trees and you can go and put a tape measure around them at a certain height, and you can thereby estimate how much biomass and how much carbon is stored. So that's relatively easy. But when we're talking about soil carbon, you can't see it. So you've got small changes against a very large background, which make it challenging. You can't see it. So it's difficult to measure. So you can measure the changes, but because they're very small against a large background, and soils are very variable, that can quickly become too expensive. So it's more expensive to do it than the credit is to remove the carbon from the atmosphere. So you can't directly measure soil carbon at every point in space. Now, there are some techniques that are being developed which rely on spectroscopy, which are showing some promise. So we could be relying on those in the future, but they're not there yet. So I think in the interim, we have to rely on a combination of direct measurement, modeling, because we got some pretty good soils modeled, good biogeochemical models that can predict changes in soil carbon, but these need to be really well calibrated against long-term experiments. We have a bunch of those around the world. We have short-term experiments where you can test the processes. And then, of course, you need the data to run the model. So you need activity data, which measure things like management. And you can add to that remote sensing, where you can't detect the change in carbon from space, but you can detect the activities that have taken place. For example, if there's residue left on the surface of the field, or if it's being tilled or not, you can detect those sorts of things from space. So it's a matter of, we've got all the pieces to the jigsaw, I think, but we've never really fully put them together. That's because for an individual project, it wouldn't be possible to do that. So I think we need to do that at larger scales, probably at national scale, and maybe link this into national greenhouse gas inventories. If we could link up the remote sensing, the activity data, the modeling, the long-term experiments, the short-term experiments, and all of these other things that we have, the machine learning, the AI, then I think we'd have some ability, a better ability, with certain definable confidence limits of the changes that we're going to get. So I think that's the next big challenge for soil science, is developing that framework, that system, and to get that up and running. And that could be a complete game changer. You know, we think there's about 3 to 5 gigatons per year of CO2 equivalents that could be removed by the soils. But what's standing in the way of that at the moment is credible MRV.
One more thing for you, Pete. I'm curious if you could talk a little bit about BECCS, because it's a space that gets a lot of controversy and plenty of discussions about like what good BECCS would look like and how we might proceed with that. So could you maybe talk a little bit about that?
Yeah, I think with any solution, there's 99 ways of doing it wrong and one way of doing it right, So you can find lots of ways of doing BECCS wrong, in a way that competes for land at very large scales, that relies upon too much energy input, so that you're not really getting any benefits from it for the CCS component, that is too costly. But I think BECCS can work as part of sustainably managed landscapes. I mean, the first one, which is a no-brainer, is to take current things that are currently treated as waste streams and to use that, because there's going to be no land competition for those resources. There are, however, implications. Even that's not a free ride, because there are implications for that material not going back into the soil, increasing the soil carbon. So there's trade-offs there. But as part of sustainably managed landscapes, I think bioenergy and BECCS does have a role to play, and that can be done. The big issue, of course, is growing the feedstock for the bioenergy. which goes into the BECCS. And again, if you're going to have to rely on hundreds of millions of square kilometers or hectares to do that, then that could put you into serious issues.
Right.
So there's a question from Shannon on the chat, which was, is that gigatons CO2? Yes, that's CO2. So it's about 1.3 gigatons technical potential for carbon and about 3 to 5 gigatons of CO2 per year.
Awesome. Thanks. All right. Turning to Evan, I want to ask you about something that you brought up, or you recently wrote a paper about a topic that's often brought up in the carbon utilization space, that being taking carbon pulled from the atmosphere from direct air capture and synthesizing sustainable aviation fuel to decarbonize air travel. So I just wonder, I mean, this is a big topic, but what were your takeaways and how did you approach the project?
Big question is, how much do I talk about now and how much do I talk about in 40 minutes?
Just give us the basic intro and what your basic takeaways were from the project.
Absolutely. So it may have, those of you in the audience may have wondered, why did I say I worked on hydrocarbon fuels in a net zero energy system on a panel on carbon dioxide removal? Well, as John said, one of the major potential applications of carbon dioxide removal is carbon utilization for synthetic fuels, because if you take carbon dioxide, mix it together with hydrogen that you've gotten from some net zero carbon source, stick those two things together, and well, then you've got a net zero hydrocarbon fuel, because when you burn it, the carbon dioxide just goes back into the atmosphere where it came from. And let me know if there are technical issues, because I think anyway, let me know. There's some things on my end, but hopefully it's coming through well on yours. So, excellent. So I was looking at this question of, well, if we wanted to make net zero aviation fuels, how would we go about doing that, and how much would it cost? And that's a difficult question if we wanted to have net zero emissions energy, because of course direct air capture takes a fair amount of energy coming in. Electrolysis of water takes a fair amount of energy. If we want to run it, we basically would have to run it on renewable electricity. And renewable electricity, of course, you know, it's variable. It's available at some times and not others, but direct air capture, the technologies we have now are fairly capital intensive, as are some of the fuel synthesis technologies. And so we probably would want to run components of the system much more often than the electricity is available. So the question then becomes, how do we operate? How do we construct and operate a system that's basically running on variable renewable electricity to cost effectively produce, at least as cost effectively as possible, synthetic liquid fuels using this capital intensive equipment? So I view this really as an approach of, through what's called techno-economic assessment, using optimization as a tool. So it's setting up a big model that says, how big do we build all these different components? And how do we operate these components? And what about the storage of the intermediate products of the hydrogen, the electricity, carbon dioxide? How do we put all those things together and figure out how much it would cost to make these synthetic liquid fuels, figure out what are the most important drivers of those costs? Where should we be focusing our research, development, and deployment dollars? And figure out whether it actually would make more sense to just keep using petroleum-based jet fuels and offset with direct air capture with sequestration. Because of course, if we're pulling carbon dioxide out of the atmosphere to put it into jet fuel, we could also just use jet fuel and then pull the carbon dioxide out of the atmosphere at another place in time. So the basic conclusions that I came to from my study, which has been accepted, and I'm reviewing the proofs today, thank you. And I can include a link to the DOI, which will not work yet, but will hopefully work in a week or two. And the main conclusions are that this technology is something that probably could be competitive with biofuels in the maybe 10 or maybe more years. And then please stop me if I'm going on too long. And at the same time, until we get to maybe in 30 years. And if there's an enormous amount of uncertainty in what 30 years is going to look like. But and probably for the next decade or two, it'll actually be more cost effective to just continue using petroleum-based jet fuels and offsetting with direct air capture with sequestration. Once we get to really cheap hydrogen, really cheap renewables, and really cheap direct air capture, then we might get to the point where we're actually at cost parity with fossil fuels, period, which I was actually surprised by. It started the analysis. I didn't think I would come to that conclusion. So I'll conclude there.
Awesome. Thanks, Evan. Nathalie, I'm very interested to hear more about, I mean, we know life cycle analyses are crucial to any CDR approach. And I know Climeworks came out with a life cycle analysis earlier this year that got a lot of buzz. But so I'm just, how did that get created and what were the big takeaways and what are your personal thoughts on it?
So the life cycle analysis was not done by us, it was done by the University of Aachen, but we provided them the numbers. So numbers meaning energy consumption, weight of metals, weight of sorbent, so all material flows into our system. And one take-up, which was not a surprise, is that it's really dependent on the energy you use. So if you do DAC, it's very important to go to renewable energy. Everything else does not make much sense if you want to remove CO2 out of the air. You're still positive. So even with coal-fired energy, you are positive, but not that much anymore. And our biggest plant we are building just now, so it will start next month, remove CO2, is located in Iceland. So Iceland is very good in two ways. So the energy is very clean, so geothermal energy is very clean, and there is a very advanced storage site where the CO2 mineralizes very quickly. And there we came up with numbers below 10%. So if we capture 100 kilos, we emit 10, which is pretty good for the stage we are today. And also in our research, we are focusing on this. So if we are developing a new material, we need to make sure in a very early stage that it's a clean material. Otherwise, it will really jeopardize the whole LCA because the material degrades, so you need to exchange it after a certain time. So it appears more than once in your LCA. This makes it very heavy, I would say. So looking at DAC systems based on sorbent technology, there are three things. One is energy. I would say about 1/3 is coming from energy. The other one is material, so sorbent material. And all metal is rather minor because you can recycle a lot of it. So doing research, we really focus on the sorbent material itself and on the energy we are using. So this also restricts where we want to place our plants. So we want to go where electricity is clean and storage is close.
And maybe can you talk more about the mineralization process that Climeworks uses to store that captured CO2?
Yes, but I'm not the expert there. So there we team up with Carbfix. So Carbfix is a company which is located in Iceland. What we do is we dissolve the CO2 in water in the geothermal power plant, where it's then pumped back under the earth. And Iceland has very good conditions, so it's hot and the stone is very good. So it mineralizes within, I think it's days, so 2 days. That's what I have in mind. If you think about the EOR system, so a lot of time the CO2 uses to dissolve in the water, which we do already before pumping it down, which has some other drawbacks, but in terms of a fast mineralization and a very secure storage, this is a good thing to do. And I think if you want to have more details about the Carbfix process, it's very well described. I think they have some papers out. I can try to post the link.
Awesome. Well, thank you to all three of you. This was a lot of fun. So we're going to transition now. It's 1:30 to the portion of the panel where anyone who's watching can be invited up to ask questions and interact with the panelists face to face. So I know Julia is helping with letting people up, but I think there's a button where you can share your video and audio somewhere around the top of the screen. So we'll let you up and you can ask your questions. So I see Jonas is already being let in.
Hey. No. Hey guys, I don't actually have a question. I was going to ask about some of the AI stuff that David was working on that he described, and I actually read the section of the paper he described. So I'm good. Next.
Okay. I'm pulling up Will here. Thanks, Jonas.
Hi guys, I appreciate that. A question for Pete actually. So very specific, but so a lot of the world still uses fertilizers as of the Green Revolution. Do you know any papers or just your general thoughts on how you could still use stuff like regenerative agriculture to sequester carbon, but still also use fertilizer, or is that just like a no-go?
Yeah, so there is an embedded carbon cost in any fertilizer that we use. So there's a certain amount of energy goes into the fertilizer, and there's a certain amount of N2O released during the process. In addition to that, there is N2O released at the field when it's applied to the field. So the more we use synthetic fertilizer, the more that's in the balance in the LCA, the more that shows up on the negative side. So we really have to minimize the amount that we use. So agroecological ways of doing it, or regenerative agriculture, is building the soil organic matter to provide those nutrients, to retain those nutrients in the soil. So it's a no-brainer, really. It's just good agronomy, good practice, which also has benefits for the LCA.
All right, Thomas.
Hi guys, how you doing? Thanks for organizing the event. I had a question, John. I was watching some of your videos the other day, and then just listening to Pete here. Wondering what the group's thoughts are on ecosystems and biodiversity in general. It seems like we're in a gold rush for carbon and carbon offsets, and wondering how the general, what your thoughts are on ecosystem services and natural climate solutions, how it plays into the role in this bigger carbon quest.
Great question. So if you just look at it with your carbon blinkers on, you may come up with the wrong solution, which isn't a nature-based solution. So there are lots of land-based solutions that aren't nature-based solutions, because nature-based solutions also have to co-deliver not only to climate change mitigation, but also adaptation and societal benefits. So you can have some really dumb ways of doing land-based solutions that aren't nature-based. But if you think about, let's just take afforestation as an example. If you're reforesting with native trees that is the natural climax vegetation in that region, and you're involving the local communities, and you're providing connectivity within to other habitats within the ecosystem, then that's going to be good for biodiversity and good for people. But on paper, it just appears as the same thing as just planting monoculture, plantation, production, forestry. So that's really the thing. You have to make a decision, a trade-off between that fast-growing stuff, which is maybe not so good for biodiversity and local groups, local populations, and you have to balance that with the other issues. But that's usually, as I say, there's one good way of doing it, or a few good ways of doing it, and quite a few dumb ways of doing it. And you can bet your bottom dollar that we find the dumb ways.
I got to use that.
Okay.
I actually have a real question now, if that's okay, John.
Sure.
Yeah, it's for Nathalie. What you're doing with Carbfix sounds extremely interesting and unsubsidized, because Class 6 wells are the way to get LCFS credits and 45Q credits. Is that kind of saying that you think that's the future, using mineralization as the key storage direction, or sequestration direction?
Yeah, I think it's a very good solution, but I don't think it will be the only one. So there's a lot of CO2 which needs to be stored. And there are other places like Iceland, so Oman, for example. But I think we need to use all storage space we have available, because we need to store a lot of CO2. So I think there will be a portfolio of storage sites in future, being oil fields, methane fields, subsea, saline aquifers. So I think we really need to explore everything we can.
Yeah, so you guys are not just going to focus on one sequestration direction. It sounds like you're exploring them all.
Yeah, so for the moment, this is our technology of choice, because there's really clean energy and they are really good conditions. But we are also in discussions with Norway. So they have this saline aquifers, which are being, I think that they build up the whole infrastructure to be the storage site for Europe. So we are open. What we don't want is to do enhanced oil recovery, for example. We don't want to produce oil with the CO2 we store, but we are not restricted to one technology with respect to storage.
Sorry for that scream. If you guys heard that, I think my son just got off the wait list for his college of choice. That's my wife. Either that or she's dead, one or the other.
And thanks, Nathalie.
Thank you.
I think Daniel's next.
Hi. I just had a question on the kind of storage processes. I'm aware that mineralization is obviously a really great long-term storage option because it's a rock, I guess I was also wondering, given the longevity of plastics in a lot of situations that's currently wreaking havoc on ecosystems, is there any research into just polymerization of anything that comes off of like any kind of carbon capture compounds that are formed? Like, I think the direct air capture with amines produces like a carbamate, and so if you could make a polymer out of that, then you could potentially store that in similar spots that weren't necessarily the best for, or didn't have the conditions for mineralization. Is that something that that you guys are aware of?
So you mean to have the reactants in the machine and then store sorbent together with the reacted CO2?
If the sorbent is easier to, takes lower to produce than it does to actually like regenerate after you've removed the CO2, then could you store the combined product of the sorbent and the CO2 and then just make more sorbent?
So I think we are not looking at this, but as I'm aware that there are other companies doing this. I think it's called enhanced weathering. So they have the material reacting with the CO2 and then they store the reacted material. In our case, we really try to regenerate the sorbent because the sorbent is normally a pretty expensive and, let's say, an engineered material. So it's pretty expensive and we want to have it as long as we can.
Thanks.
Awesome. And then Ross.
Hi, I work for Google, and the characteristic of the problem you're describing, which is we need to like co-locate energy input and infrastructure and storage in a way to make this work, sounds really familiar, because that's exactly the kind of problem we run into with data centers, where you need to have cheap, hopefully clean energy, internet, and a population that can run a data center. It seems like the same problem to me. And one of the things that tends to govern locations of data centers is, the combination of two of those factors that are really critical, and that is energy and location. And so I'm kind of curious, because carbon capture is so much of a bigger problem than locating data centers in the sense of the amount of gigatons of material that ultimately needs to be moved. So I'm from Canada. We have clean energy in the form of hydro up north and nuclear in the main population centers, and the energy is cheap there. In fact, I think in Labrador with hydro, you can get it for under a penny a kilowatt hour, because the only way they can sell it is to ship it through Quebec, who, of course, slaps a big tax on it. So if you want to get cheap hydro, locate in Labrador, and if that could be used to drive some of this stuff, you might be able to make a decent business with carbon credits if the rock formation there works. And so I'm curious really about if, let's say, the next generation nuclear energy actually meets its promises and comes in cheaper and cleaner and all that, where would you actually locate your sites? If you could move the energy anywhere to where you need it, where would be the best sites on the planet to do this? Because ultimately we want the lowest cost way to sequester a whole lot of carbon.
That's a very good question, and we are, or not only us, but many people are trying to find the best location site. So I think they are the most obvious ones. So empty oil fields, empty gas fields, which we know work. Then we have these sites like in Iceland. They are similar conditions in Oman, but I think where the best sites are still under investigation. So I'm not a storage expert, but I think there's a lot of research ongoing in storage as well.
Thank you.
Awesome. Thanks, Ross. All right.
Oh. Mind if I respond as well?
Yeah, jump in, Evan. Thanks.
So Ross, I think you're absolutely right that the question of where do we put direct air capture and where do we put data centers, where do we put fairly capital intensive, energy intensive systems are very similar problems, and in a sense they're kind of all big optimization problems, as Nathalie pointed out. Well, we want cheap energy and we want it to be close to somewhere we can put the carbon dioxide. And it's another major factor in some cases will be water. We can get some of the cheapest solar energy that there is in giant deserts in Australia, for example. That said, we wouldn't have water that we would need for some carbon dioxide removal systems, but not for all. So as Nathalie will can doubtless talk more about than I can, the Climeworks system, as I understand it, actually produces a bit of water in the process. The carbon engineering system operates at a high temperature, requires a fair amount of water, and this is one thing that I looked at in my paper, and I was a little bit surprised. Even if we assume that we're using desalinated water and maybe even build a pipeline from the ocean over to wherever we are, it actually doesn't increase the cost that much. It's like 2% of the cost of a synthetic liquid fuel. So I think that there are real possibilities for large scale, at least utilization of captured carbon dioxide in places that may be really just optimized for resource, for solar resource. If we want to optimize for sequestration, then of course, building carbon dioxide pipelines is super expensive, and we'll probably want to put at least those two things next to each other.
Cool, thank you.
Thanks, Evan. Thanks, Ross. Hi, Rohit.
Hi, John. So maybe just a comment, part question. So for Nathalie and Pete, having done quite a lot of thinking about which DAC direction I want to take, I'm very much bending towards Pete and nature, because it feels that if we're going to scale something, we need to do it in a materials light and energy light manner. And I think certainly where I'm thinking, it's also cheap cost of land, doing it in places where there's a lot of young people, and you want to create jobs for the next generation, and there's a social element to all of that as well. And yet, so I'm sort of going off in this direction for a nature-based DAC approach. And the one thing that I think is quite interesting is that this is not a criticism, we need to do everything, but it seems like for conventional DAC, there's a lot of energy, there's a lot of steel, there's a lot of materials, there's a lot of permitting and everything else. And it seems like it's always going to be difficult to get it under, say $200 a ton, or whatever the number is, right? There's a lot of construction and a lot of everything. Whereas if we can find cheap, organic, nature-based solutions, then maybe $50, $100 a ton is quite doable. Just want to understand what your comments are, because you're letting, I mean, in one way, you're letting nature do the work. In another way, you're letting microbes do the work. So if you take a bio approach, microbes are doing, the effort.
I think if we can use nature to get those nature-based solutions, that's the way to go. I don't think it's at the expense of technological solutions. I think we probably need both, because they're scalable and can be used in different locations. They're units that you could just drop just about anywhere on Earth and make them work, subject to the other things that we talked about, access to safe storage and such like. But the nature-based solution, because they provide potentially, if they're done well, all the co-benefits, then it seems like a great idea to use them. But there's a trade-off between the fact that they're cheap and this poorer durability. So you do have to trade that off. In a way, you could regard it as a poorer quality carbon storage because it's only there for years, decades, it's potentially reversible. So I think we have to have a mature discussion about that. I personally think that we should use nature-based solutions just because of the co-benefits. If they don't work for carbon mitigation in the way that we envisage, we've made the world a better place without storing any carbon, but we still made the world a better place. So that's really identifying those where we're going to have the maximum co-benefits, with hopefully some climate mitigation as well. In addition to the technological solutions, which can be applied, in a modular way around the place. So I don't see a competition between the technology-based and the nature-based ones. They've got advantages and disadvantages, and I'd like to see us. This is a massive challenge. We've got to get to net zero by 2050. We're going to need all the tools in the box, I think.
Thanks.
Cool.
So I completely agree. So we need a lot of different ways to tackle the problem, and each technology or each solution has pros and cons. And if we have a portfolio of different solutions, it will be best. So I think we need to do everything we can with every technology and solution we have.
Yeah, okay, but there is a limit on capital, and that's something that I was thinking about the other day on Twitter with guys who run LanzaTech. They've taken, it's a fantastic company, but it's taken a long time and $400 million to get to that particular point in time. And I think we have a limited amount of climate capital around, so we can't chase everything. So you need to get to these points where you actually stop doing stuff. And maybe at the moment we're not in the stop doing anything frame of mind because we haven't solved it. But if you were looking at this as a single company, and if you're the president of the world, which you obviously will be in due course, John, you'll be able to say, do this and don't do this. You'll have to make mutually exclusive choices. We're not there yet, but I think we might have to do that at some point in time. And so there's no point in going down this very intensive path. Let's try and do something which has, as Pete says, a lot of co-benefits, which is maybe cheaper. So that's just my long-term thinking around maybe strategic choices that we will potentially make in due course. Okay, cheers. I'll go and hide now.
Thanks, Rohit. Question, feel free to hop up, anyone who wants to ask questions. Otherwise, I'll just pull from the chat. Tay or Ty Lim just asked, from my understanding, Julia's up. Hi, Julia. Do you have a question?
Is it working? Okay. So this is a slightly different question. Since this is a forming ideas panel, I was wondering if over the course of the past 50 minutes, any of you have found some sort of intersection between what another panelist has talked about and your own work.
I would say yes. Evan talking about AI. AI has not been fully exploited in this space, and I think it could be put to work a lot more, particularly with the ARV thing that I talked about. When I was riffing about MRV, I thought about AI at the last minute and added it in because it sounded cool. But I think that's really got some potential there, along with the modeling, data assimilation, some AI, some machine learning. I think that's got a great potential for pulling all this information together in MRV. And what Nathalie's described, I've also, although I focus on nature-based solutions, I'm also extremely interested in DACs. So as I said, I don't think you don't have to choose between them. I think we're going to need both. So I see some common ground there as well.
Absolutely, and Pete, I would say that in particular the question of of monitoring and verification of soils over large areas, sequestration in soils or forests elsewhere. This just screams remote sensing. We've got satellite imagery in the optical bands, in all sorts of electromagnetic bands, and to the extent to which we could collect ground-based measurements and start doing correlation between what we can see from space and what we can see on the ground, I think that could help us give a really good idea of how much is in the ground.
Awesome.
Great.
Hey, Thomas. Oh.
Hey, I just want to interject on, how do you say it, Julia?
Julia, yeah.
Yeah, Julia, in combining all the different ideas here, in the U.S. we have in the land use codes planned developments or planned unit developments of how you come in with big chunks of land, and you might be a residential subdivision or commercial development or industrial development. What do you guys think, combining all these different ideas, what do you think about the concept of climate development or carbon development, where you actually put a bunch of these uses on one property? Assuming the property is big enough and the location is in the right spot, but you combine nature-based solutions, direct air capture, energy storage, climate resiliency, green infrastructure. I mean, it'd have to be the right property, but that's in real estate development world, that's how you look at it. You say, okay, what's the property? What's the use? And what do you think about combining all these things? And do you think that's overkill, or do you think that could be beneficial?
For demonstration purposes, that would be great to have all these things co-located, because then you could compare them side by side. So I think it would be a great idea. But there's a danger that if we just look at it through climate or carbon blinkers, then we could end up with, we say this is a certain, a carbon capture farm, then we forget about all the other ecosystem services that are provided by that land. So I just think, I always have to remind myself, being a carbon nerd, I have to step back a little bit every now and then and say, there's more to the world than carbon. I have to force myself to think that and think about all the co-benefits so that we can get the maximum benefits out of what we do.
On co-benefits, do you think co-benefits should be mandatory? Instead of just the focus on carbon offsets or carbon captured per ton, tons captured, whatnot. I mean, should there be some sort of regulation or requirement, even if it's intrinsic, to what we're all doing, where there has to be co-benefits, like to what Nathalie is doing in Climeworks. I mean, should there be some sort of rating related to co-benefits, not just to tons of carbon sequestered?
Yeah, I think the bare minimum would be do no harm in terms of the other ecosystem services that are provided. That should be mandatory. But then anything else that you can provide as co-benefits, I think, make the project more attractive. So the more co-benefits you can promise or you can deliver with the project, the more that would be attractive to the large corporations that want to fund nature-based solutions to help hit their net zero targets. So I think it wouldn't necessarily have to be mandatory. I think do no harm should be mandatory, but all the other ones give you a competitive advantage for the project. So I think the market would take care of that by itself.
I also think one needs to look at it in a holistic way. So one thing is the efficiency. So I think our system is pretty efficient if it comes to land use. However, it needs energy. So looking at the LCA and looking at all aspects, I think this is how it needs to be done and how it needs to be compared. So one thing needs a lot of land, the other thing needs water, one needs more energy. So I think creating co-benefits is very hard to quantify. But I agree with Pete's statement that the no harm is the most important. That's also why we do this LCA quite thoroughly.
And what's LCA?
Life cycle assessment. So it assesses how much CO2, for example, so the carbon footprint of your technology, but it has also a lot of different factors in it. So I think land use is one, acidity of waters, and so they are about, I don't know how many factors which are assessed, human toxicity, and all of these give like a picture of the technology or the solution you have.
Okay. Great, thank you.
Awesome. I want to ask a question that came up with Kate Levy and Tay in the chat about, for all the chemical engineers who are listening in, about for Nathalie, what barriers are there to making the process faster, and are there major benefits of making the process faster?
Yes, so I think we depending on the sorbent you're using, you can have very fast processes and slower process, and it's always a trade-off between energy and production. So if you have a very fast process, you need to think also about the energy you need to heat up your system. So you don't only heat up your sorbent, you have metal you heat up and more stuff. So if you have a very fast system, in general, you need a bit more energy because your system needs to heat up fast more often in a year. And I talked earlier about our portfolio of sorbent. So we have systems which are very fast. So they are, I would say, in the range of 15 minutes, one cycle. We have others, I think that's the one you're referring to, it's about 4 hours. So it's really depending on the kinetics of your sorbent material. So it's an optimization problem between energy, production, and at the end it boils down to the cost. So what is the cost of ton of CO2? Does it make sense to make it faster or not?
Cool. Kate has a follow-up question about counterflow, but maybe you could address that after. I think since we're wrapping up, maybe an interesting thing to do would be just like final words from each panelist and the final, sentiment that you all want people watching to take away about where we are right now and where we're going. So I guess we'll start with Evan.
Sure. Well, let's see. For this panel, I'd say this is an incredibly important space, as I think
important space. All right, hopefully you can rejoin us. Pete, you want to start us off?
Yeah, right. We've been hacked, right? They cut him off in his prime. So yeah, I would say that nature-based solutions are great. We should exploit them as far as possible, but we can't rely on them. The land can't do it all. So in this space, I mean, I know you all know this, but I just say it again, just to hit it home. We really have to reduce emissions aggressively and immediately. That's the bottom line. And we then use CDR, all the things that we've been talking about today, just to address the final residual emissions that we can't really get at in any other way. So we're the last resort, I think. We shouldn't use CDR as a replacement for immediate and aggressive emissions reduction.
Well said. And Nathalie.
Yes, I completely agree with you, Pete. So I think we need to reduce emission, and the other thing is we need to upscale the technology we have really quickly. So we spend a lot of time in research, but we never made the step to big scale CDR. And I think it's time to do it, even if the technology we have today is a bit expensive, but we can't wait anymore. So we need to do research, but we need to upscale, and we need to do it now.
Well said. It's a good note to end on. All right. Well, thank you everybody for coming. I hope this was a fun and informative panel. Plenty more coming throughout the day. I think that Evan got pulled off to his next panel, according to Julia. So you can go check that out, or I think there's a different one happening as well. But thanks, Pete. Thanks, Nathalie. This was a lot of fun.
Okay, thanks a lot. Bye.
Thanks
Bye.
a lot. Bye-bye.